Hello, I'm Nathaniel.
Hi, I'm Tamanna.
And we're
We are
Design of Machine Element TAs. And today, this is Gear Lab.
Today we are going to become familiar with the different types of gears used in machine systems and their importance in design decisions. Gain experience selecting appropriate gears from catalogs for a specific application. Understand the kinematics and kinetics of common gears. Design and analyze a simple transmission. And finally, extrapolate knowledge obtained from lab to different applications and design constraints.
We will be going over 3 different lab stations to examine gears individually and within systems. But first, a brief overview of gears. Gears are machine parts with teeth, which, in general, transmit torque at a speed and direction to another gear or toothed part. Gears are a high-efficiency means of converting speed into torque mechanically.
Gears are generally manufactured through the process of hobbing a gear. When manufactured, there are 3 principal measurements one should keep in mind. Gear thickness, which along with material determines the maximum amount of force a gear can transmit. Pitch, or the distance between points on teeth. Diametral pitch here in America and module everywhere else. And finally, the number of teeth. To illustrate pitch, I have a couple of gears with an involute profile, a 12-tooth gear and a rack gear with infinite teeth. Think of a really big gear, then look at a close-up section. Note on the small pinion gear the curved involute profile of the tooth, and on the rack the straight profile of the tooth. These represent the extrema of gear profile, however, both have the same pitch. Now that we have covered the basics of gears, let's get into some of the specialized types of gears out there. Spur gears transmit motion from one shaft to another parallel shaft through teeth that are parallel to the axis of rotation. When spur gears mesh, we can see that the force is transmitted along the point of contact between the power gear and the output gear. Note that as we move from one gear to the next, the direction of rotation is reversed.
Let's take a brief look at a simple 6 spur gear transmission system. If we know the input speed of gear 1 and either the ratio of teeth or pitch diameters of gears 1 and 2, we can determine the output speed at gear 2. With these same ratios, gears can be chained together to form a single input, single output gear ratio. Keep in mind that for a given gear ratio, the output speed and output torque are inversely related for a given input. Using gear ratios, lowering speed at an output raises the torque at an output, and vice versa. Let's take a brief gander at the gear ratio in a manual car transmission.
So in low speed, we get the greatest leverage by letting the smallest gear on the counter shaft turn the largest gear on the drive shaft. The engine on this model is running at a constant speed of 90 revolutions a minute. With low gears in mesh, the rear wheel is turning at 30 revolutions a minute, about a third the speed of the engine, but with 3 times the force. The power is going through these gears in the transmission. After we've started the car rolling, we want fast pickup. So we shift into second by sliding the sleeve backward to mesh with this gear on the shaft to the rear wheels. The wheel is now turning at 60 revolutions a minute, and the power flows through these gears. For higher speeds, we let the power go directly to the rear wheels. We shift the sleeve forward so that it meshes with the shaft from the engine. The power travels straight from the engine to the drive shaft. Now the shaft to the wheels is turning at 90 revolutions a minute, the same speed as the engine.
Helical gears have teeth inclined to the axis of rotation. They are quite similar in operation to spur gears, but in practical use, they are much quieter than their spur gear equivalents. In addition to having better tooth geometry for load capacity. This at the expense as well as a thrust along the gear axis, which increase wear, use plenty of grease, and lower gear efficiency. Bevel gears are much like spur and helical gears and are used primarily to transmit motion between non-parallel, often perpendicular shafts. By virtue of having teeth on conical surfaces as shown. Worm gears are comprised of the worm, that is, the screw-type thread shown here, and the worm gear. Worm gears, like bevel gears, transmit speed and torque to shafts at right angles, but unlike the bevel gear, this transmission is one-way.
As a great engineer once said, you don't spin the worm spins you. I am applying as much force as I can to this vice grips, but Tamanna is just getting the better of me here. Even if she stops spinning the worm for a minute, if I apply all the force that I've got on here, I can just barely spin the worm gear. This is a one-way transmission system, to be sure.
Another quick note regarding the worm gear is the method by which one counts worm gear teeth. Remember, to count worm gear teeth, you should look at the front of the worm rather than the side. Is where a worm's teeth are easiest to count. In the following diagram, worms with 1, 2, and 4 teeth are shown. Keep in mind, when running with this transmission, that the worm always spins faster than the gear. Spur gears can also be arranged in such a way as to keep the input and output of a shaft aligned. This configuration is generally known as a planetary gear set.
The center gear is known as the sun gear, and the gears which orbit are known as the planetary gears. Planetary gear systems are commonly found inside of automotive gear transmission systems, as this configuration of gears allow for automatic transmission without gear shifting. To demonstrate this, I've provided a set of 2 devices to look at. A 1 degree of freedom system here, this sprocket set, and a 2 degree of freedom system set over here with these planetary gears. Degrees of freedom are the number of inputs required to fix an output in a system. So on this sprocket set, you can see that I'm putting in an input, and I get out a single output. On this planetary gear set, we can go a multitude of different speeds. This planetary gear system has 2 inputs, which together can be used to modulate the speed of the outer gear. Holding the sun gear fixed while moving the planetary gears cause the outer gear to rotate fast. Holding the planetary gear fixed while moving the sun gear will cause the system to rotate more slowly. Finally, by carefully modulating the rotational speeds of the sun and planets, the stars align to a fixed outer ring. Again, changing the torque and speed of your vehicle of choice, all without changing out or shifting gears. Systems with more than 2 degrees of freedom can get quite chaotic.
So for the gear overview, let's head over to the station 1. Before you start, make sure you have the lab manual and and your writing utensils ready.
Hello and welcome to Station 1. Here you can see a fine selection of gears before you. Let's turn your lab manual to station number 1. And right under here, in the gear type column, you see that the first gear is a spur gear. Looking through our gears, you can see that number 4 seems to be the corresponding number for a spur gear. So what we're going to do next, after we've written a 4 in the corresponding number column, is we're going to draw a Freebody Diagram of this gear with its mate. So let's do an example of that. Why don't you head over with me to the Board of Science? Hello, and welcome to the Board of Science. Today, we're going to be looking at the force interactions between two spur gears, spur gear A and spur gear B. Now, I'd like to make an assumption right off the bat here that spur gear A and spur gear B are identical, having the same number of teeth and the same pitch. Now, if we could, I'd like to use the power of Cyborg CAD to do a little bit of a zoom and a rotation here just to look at these two teeth right here. There we go. Excellent. So, before we begin, I would like to call out my assumed coordinate system. So I'm going to call this direction X, and I'm going to call this direction Y. Just so we're on the same page here. Now looking at these gears, I'm not quite sure what's holding them up. I think we need a couple of reaction forces on each of them, don't you think? So I'm going to put in a reaction force here on gear A, at gear A's center. I'm going to call that RAX. And I'm going to call this RAY. Similarly on gear B, we're going to do the same thing. Give it a couple of reaction forces. RBX and RBY. Excellent. Now, between gear A and gear B, we have some forces and interactions going on here. We know that a force of contact is going to act perpendicular to the area of contact. So we're going to look at our area of contact right here, and we're going to draw a force perpendicular to it. So we're going to have gear A acting on gear B for a contact force W. Now we know that gear B, therefore, is going to exert an equal and opposite force on gear A. So we're also going to draw another W here. And it's equal in magnitude to this W, but opposite in direction, of course. Now I can split these W's into components. This one, we have a W radial component, and a tangential component. Similarly down here, we have a radial component and a tangential component. Nice. Looking at our forces, I think that just about covers it. But wait, there's a little bit more. We've got this one force right here. It's a force acting at a perpendicular distance to the center. So we've got a force in this perpendicular distance. So we'll call this perpendicular distance D. As you well know, a force times a perpendicular distance is going to give us a moment, or as we know in dynamics, we'll just call it a torque. We've got TA acting here. As I said before, a torque is a force times a perpendicular distance, so I'll write that down here. TA is equal to the tangential component of the force of contact times D. Let's break that down a little bit more. I'll say that the angle between the force of contact and the tangential component of that force of contact is a Greek letter. Let's call it phi. We'll make that represent the pressure angle. That's what we'll call it. So, pressure angle. So down here on our equation, we can just write W cosine phi times d. Now remember, we've got a torque acting here, so therefore we should have a torque acting here. This concludes the free body diagram for two Spur gears interacting.
Now take a look at gear number 1. What does this gear look like? It will engage like this. Now you will draw a free body diagram of its operation with another gear. Now take a look at gear number 2. Wow, what a large number of teeth you have. Now here is the gear and its partner in situ. Now you will draw a free body diagram of its operation with another gear. Now take a look at gear number 3. So there's a nice looking keyway and set pin on this pair, and the interaction like it works like this. And you'll have to draw the free body diagram of this in operation. Now take a look at gear number 4. Oh, I see, you have already done that one. Now let's head over to gear number 5. So where's the contraption? So this should be an exciting yet familiar free body diagram. Nice. Let's get a wiggle on to station 2, the black box gearbox, or the BBGB for short. Now let's figure out what's going on. Let's see now. By examining our footage, we have a rotational output speed of about 7.22 RPM. That's about all we can do for now. Okay, now we'll open up the machine. Inside we can see the drivetrain. I am going to discombobulate the assembly, count the number of teeth and calculate the gear ratio. Okay, I have arranged each of the gears here for your viewing pleasure in a single still image. Okay, let's check your math. I have brought out the photo tachometer. A bit hard to read on camera, but trust me, it is reading about 4000 RPM. Does this match your theoretical input motor speed? And what is the percent difference? Now, the third station of the lab involves disassembling a Kitchenaid Mixer, investigating its gear train, and then reassembling the mixer. Now, looking at the exterior of the mixer, we can see a rotating shaft for a steel mixing beater, a bowl for containing, and curious removable portal in the front. Like this one.
Now, let's disassemble the Kitchenaid Mixer. First, I'm going to remove the bowl. Set that aside for later. Use the right screw. Whoa! That's a lot of grease. Wonder why. Let's get this cleaned up. And there you have it. One cleaned and freshly labeled Kitchenaid Mixer. Looking at the internal assemblies, we have a motor, which connects to a gear here, labeled Gear 1. Gear 1 connects to Gear 2, which connects to another gear, which then turns this assembly, marked 3. Gear 3 meshes on the top to this gear right here, Gear 4, which is housed in this aperture assembly right here. Then finally, underneath the mechanism, we have the
Gear 5 and 6 assembly.
I guess all that's left now is to put the thing back together. Hey guys, thanks for attending Gear Labs. Okay. That's not too bad. Okay, I think we're good.
So, should I start?
Yeah, we should start.
Hey Nathaniel,
Hey Tamanna.
do you know why was the manual car set shifting gears?
I don't know, Tamanna. Why was the manual car sad shifting gears?
Because the clutch was depressed. Oh my God.
Okay. Serious. Hey Tamanna,
Hi Nathaniel.
what did the Planetary Gear say to the Sun Gear?
I don't know.
I don't know. If I was you, son, I'd spin the other way.
Okay. Oh my God. What do dentists use to drive their toothy gears?
I don't know, Tamanna. What do dentists use to drive their toothy gears?
Brushed motors? Oh my God! Is it too bad?
No, it's pretty good.
Okay.
What? Where'd it go? What did you do? I walked away for 1 minute. What did you do?